In this section, we are going to talk about linear impulse and linear momentum. You all know that Newton's second law is some of the forces that we have on a mass is going to be equal to that mass times the acceleration of it. And we call this Newton's second law. You can write acceleration as dv dt. And also, if the mass is constant, you can write this as derivative of mass times velocity divided by dt. Because mass is constant, you can take it out of this derivative or you can bring it in. Both of them are the same, right? And we have a new definition here. We call the mass times velocity the momentum of that mass. So whenever we have a body with the mass of m, which is moving with the velocity of v, then the mass of it times the velocity of it is the linear momentum of it. So the linear momentum is, which we usually show it with g, is equal to the mass times velocity of that particle or that system. So if you replace mv with that g, so this is going to be the g, or derivative of the linear momentum dt. Or you can show it with g dot. Actually, this is a more general equation for Newton's second law. Because if you write sum of the forces is equal to mass times acceleration, this is true for a system which the mass of it is constant. But sometimes the mass of the system is not constant. For example, if you consider a rocket, when the rocket is moving, the mass of it is continuously decreasing. So if you want to write the Newton equation for the rocket, then sum of the forces is not going to be equal to mass times acceleration because mass is not constant, it is changing. And we cannot write it as mass at any moment times the acceleration of it. That's going to be wrong. But for the whole rocket, we can write sum of the forces is equal to g dot, which is going to lead to a different equation, which is not part of this course. Anyhow, sum of the forces is equal to g dot, or change in the momentum of the system. And we are going to do a little bit mathematical work here and come up with a different equation which is going to be useful in some of the problems. So if you consider this equation, sum of the forces is equal to dg divided by dt, you can write it as dg is equal to sum of the forces times dt. And sometimes in some systems, we know the resultant force that we are applying to that system as a function of time. So if you know sum of the forces as a function of time, then you can integrate both sides of this equation. What's the meaning of that? Let's say this mass is starting from here, from point 1, and goes to point 2. At the beginning, the velocity is, let's say, is v1, at the end is v2. It can be a mass or it can be a system, which goes from position 1 to position 2. So if I integrate both sides of this equation from 1 to 2, then integral of dg is going to be just g. From point 1 to point 2, it's going to be g at 2 minus g at 1, which means the linear momentum at the end minus the linear momentum at the beginning is going to be equal to sum of the forces dt from point 1 to point 2. So from time 1 to time 2. Let's say at the beginning time is equal to 0 and at the end time is equal to t. So if I know what forces do I have on this system from 1 to 2, then I can put it in this integral and integrate it. So the left side of the equation is going to be change in the linear momentum of the system, and the other side is going to be integral of the sum of the forces from 1 to 2. We call this integral linear impulse. And sometimes, which you're gonna see in a lot of examples after this video, sometimes we have no forces on our system from 1 to 2. So if sum of the forces on the system is equal to 0 from 1 to 2, then this side of the equation is going to be equal to 0, which means G1 is going to be equal to G2. Or in other words, the linear momentum of the system is not going to change between 1 and 2. We call this conservation of linear momentum. So if you have no force from position 1 to position 2, then the linear momentum is not going to change. Whatever we have at the beginning is going to be equal to whatever we have at the end. The mass of the system times velocity of it is not going to change. Sometimes we don't have only a single mass, we have a couple of masses. So to calculate the linear momentum of a couple of masses, a system, you need to multiply each mass to the velocity of it as a vector and then add them together. That's going to be the linear momentum of your system. How it's going to be helpful, I'm going to show it with an example. Problem 3.142. So in this problem, we have a bullet which is moving toward this box, and the box is not moving at the beginning, with a velocity of 600 meters per second. And the mass of it is 75 grams. The mass of the box is equal to 50 kilograms. Let's say the bullet is gonna penetrate into this box, then stop in the box, but at the end, because of the momentum of this bullet, everything is gonna move, right? So this is condition 1, and a few moments later, let's say the bullet is here, and everything is gonna move with velocity of, let's say, v2. So this is condition 2. And the question is, what's going to be the velocity of this box and bullet together? And also, how much we are going to have decrease in the energy from 1 to 2. So something you need to keep in mind is conservation of linear momentum is totally different than conservation of energy. For example, here between 1 and 2, because we have impact here, we are going to have generation of heat and also sound, deformation, all of those. So we are going to lose some energy, right? So the energy is not going to be equal between 1 and 2. Energy is going to decrease, definitely, the kinetic energy. And so we don't have conservation of energy between 1 and 2. But I'm going to show you we have conservation of linear momentum. Why? If you consider the bullet and the box together as your system, then if you look at this system, between 1 and 2, there is no external force in the x direction, right? There is no friction. We are going to have some force between the bullet and the box, which is going to be a huge force, but that's going to be an internal force in our system, right? It is not anything from outside of the system. From outside of the system, we have only contact force between the box and ground, which is going to be just in the y direction, right? But there is nothing in the x direction. So for our system, which is combination of the bullet and the box, we have sum of the forces in the x direction is equal to 0. And the meaning of this is based on what we just learned. The linear momentum in the x direction is not going to change. So G2 is going to be equal to G1 in the x direction. So this index x means in the x direction. In the y direction, there is no velocity, We have the same equation for the y direction too, but that's going to be 0 is equal to 0 because there is nothing in the y direction. So in the x direction, what is g2 and what is g1? So let's talk about this one first, g2. So the linear momentum here is going to be mass times velocity, right? The mass of the whole system is mass of the bullet plus mass of the box. Let's call this one m1 and this one m2. So it's going to be m1 plus m2 times v2, because both of them are moving with the same velocity, v2, to the right. How about at the beginning? What is g1? g1, we have two masses here. To calculate the linear momentum of the system, we need to multiply each mass to the velocity of it, then add them together. So the linear momentum here is going to be m1 times, which is 75 gram, times 600 meter per second. So it's going to be m1 times 600 plus the second mass, m2, times the velocity of it. But the velocity is equal to 0. So let's put everything back in the conservation of linear momentum equation. So we are going to have m1 plus m2 times v2 is equal to m1 times 600 meter per second. So we know what is m1 and m2. If you put the numbers, then the velocity after the impact is going to be equal to 0.899 meter per second. So that's the velocity after impact. But we need to calculate how much we are losing energy here, right? So we need to calculate what is T1 and what is T2. So T1, which means the kinetic energy of our system at the beginning, is going to be equal to 1/2 of m1 times the velocity of it squared, plus m2, 1/2 of m2 times velocity of it squared, which is 0. And this is going to be 13,500 joule. And at the end, T2, the kinetic energy is going to be 1/2 of the total mass, which is m1 plus m2, times the velocity of it squared, v2 squared. And if you replace v2 with 0.899, then this is going to be equal to 20.2 joule. And you see the kinetic energy decreases a lot. So N, which is equal to change in the energy divided by the initial energy, or T1, there is no potential energy here, is going to be equal to, actually multiply to 100 to make it percent, is going to be equal to 99.7%. Actually 99.9%. So the kinetic energy is going to decrease by 99.9%, which is a huge energy loss. So the point here is conservation of linear momentum is not equivalent to conservation of energy. They are totally different equations.